Again, once again, I am going to explain with the examples. So under this, we have data processing instruction. The data processing instruction, as I told, can be used for any arithmetic operation, and if we use the S suffix on the data processing instruction, it will update the carry flag or all the current processor status registers. So we'll start with the move instruction. I'll show one example program here. Okay. When we are writing a program for LPC 2148, I'm using the device here LPC 2148. So the left hand side we are giving one space. That is because when we are writing a program, the label is this first place is for label. So label position label place we have to keep empty because I am not using any label here. The next, always in program start with area. So we are telling here we are reserving one area. The name of the area is here example. Okay, we have to use this name other than any mnemonics which we are using in the program. Next, this area is for code memory. Code memory means we are writing a program, so in this area, and that program will be stored in read-only memory. So we are specifying that it is a read-only memory. So the first instruction I am using here, the move instruction. Okay, so move instruction R5 comma hash 0x02. Now we'll see our move instruction syntax. In the move instruction syntax, you can see there first syntax is instruction followed by condition s suffix and rd comma n. Rd is in my program what I showed just now, that is R5 is a destination register and n is a immediate data. So n can, okay, I'll show that program again. Okay, so here we have this 0x02. This is our n. So destination register is R5. Okay, so after executing this instruction, we are copying the 05 into 02 into R5 register. Next, the same type of instruction is there, that is 7 we are copying into R7, and the third instruction is different from the first two instruction because here the destination register is register and source also is register. In the first two instruction, source is a immediate data, but third one we are using source is the register. So we can use source is a register or the immediate data. So we'll see if we are executing this program what will happen. Okay, now we are in the debugging window. So in the debugging window, this arrow shows that which instruction we are executing now. Okay, I'll expand this. Okay, and can you see this R1 register content is 0, sorry, R0 content is 0, R1 register content is 0, R2 is 0, and the register what we are using is R5 and R7. So R5 register content also is 0 and R5 register content is 0 and R7 register content also is 0. So default only we are getting the stack pointer value, okay, stack pointer value also is 0. Come here, yes, okay. So now this is in mode 0x13. 0x13 means it is a supervisor mode. You can see here the supervisor is highlighted because we are in the mode of supervisor. Okay, and interrupt mask, fast interrupt mask is disabled, I mean masked. Okay. Okay, so we'll see now how the move instruction works. So according to this, after executing the first instruction, we should get in R5 register 02. So what we have written here 0x02, okay, and R5 register is 32 bit register. So you can see here R5 register holds 1 2 3 4 5 6 7 8 zeros, and this is a hexa number. So because it is a hex number, if you are checking in the bitwise, one digit in the hex number is a 4 bit in binary. Okay, so if it is 4 bit in binary, 4 into 8, that is 32 bits. So 32 bits is used by one register, but what I am loading in this instruction is I am loading only 02. Okay, so it is only 4 plus 4 means 8 bit data, but still after executing this, we'll execute this. Okay, after executing this, we can see here the R5 register content is 02. Can you see this? I'll zoom it. Okay, can you see this? The R5 register content is 02. Okay, now if R5 register content is 02, next after executing the second instruction, R5 register content is R7 register content is 7. Okay, I hope you can see this. Yeah, so the 7 is not only 8 bit, it is 32 bit. So means the remaining bits are 0. Okay, next the third instruction, it will move R5 content into R7. So what is there in R5? In R5 we have 02. That 02 will be moved to R7. So after executing this third instruction, it R7 content will be 2, because whatever there in 02, the R5 is my source register. So from this source register, we are copying the data what is there in source register to R7. So in the R7 we are getting the same data what is there in R5. Okay, we'll execute that. Okay, so after execution I got in R7 02. Okay, so this is how the move instruction works. Now the condition here in the move instruction, that is we can use this move instruction with the condition, means condition whether it is equal, not equal, zero flag is set, no zero flag is not set. So all these condition can be used to execute this instruction. Means if the it will check if the condition, like if the zero flag is set, so it is going to check this in the current program status register. I'll show that. Okay, in the current program status register, it is going to check this flags. negative flag, zero flag, carry flag, over flag, all these flags will be checked. If that flag is true, I mean it is 1, then only it is going to execute that particular instruction if I mention that condition. Okay, so okay, there is one more instruction here, that is MVN. MVN stand for move the not of 32-bit value. Means here I'll show the previous program again. Okay, here I'm copying R5 content into R7. So what was there in R5, the same copy I got in R7. You can see that after executing the third instruction, R7 content is 0, 2. Okay, so I'll change the program now. So instead of MOV, I'll use this MVN. MVN means, so it should be complementing this source value. What is there in source? 0, 2 is there. It will complement that, and the complemented value, bitwise complemented value, will be copied into R7. We'll see, we'll go to the debugging. Before that we have to build it. Okay, so okay, now okay, yeah, so I'll execute the first instruction again, that is R5, sorry, 0, 2 is moved to R5. Next 0, 7 is moved to R7. Next what? MVN, that is R5 complement value should copy into the R7. So that is FFFFFFD. Okay, now see, if I write this 0, 2 in binary, I'll write only for example point of view. If I write this in binary, it is like 0, 0, 0, 0 for first 0. Next for 2 it is 0, 0, 1, 0, right? So if I make a complement of this, okay, to make a complement of this, it is bitwise complement 1, 1, 1, 1 and 1, 1, 0, 1. So what is 1, 1, 0, 1? So 1, 1, 0, 1 is D, right? So 1, 1, 0, 1 is D, and 1111 is F. So we know that all the remaining upper bits was 0, so all the remaining upper complement value will be F. So that is what we are getting here, F F F F F F, like last one is FD. Okay, so it is complementing the R5 content and copying into R7. So what happened with the R5 content? R5 content is not changed. Okay, so R5 content is not changed, only it is when it is copying or moving the data, it will move the complemented value to the destination register. Okay, yeah, so we'll see the next one. Okay, barrel shifter. Yeah, so now you can see here R7, R5, and next we have LSL hash 2. Okay, I'll go back to the same program. First I'll come out of the debug window. Okay, next LSL hash. Okay, yeah, now again we have to do the same execution. So R5 value will be 2. Okay, next R7 value is 7. Now what we want to see is this, how it is going to use a barrel shifter. Okay, um, I made one mistake, that is I used MVN. Okay, don't need to change this. We'll see using MVN also. Before that, first we'll see using MOV. So okay, okay. So there was one error that I have not put this comma here. So now zero error. Okay, we'll go for the debug window. So after going to the debug window, yes, we'll execute this step. Okay, next second step. So now R5 is 02, yes, and R7 is 07. Okay, next as I explained, R5 content will be shifted left by 1 bit, means for the LSB bit it is going to insert 0 and MSB bit will be going out of the register. Okay, so what is R7? R7 is shifted value of R5. So that is like for 2, if you are, again I'll write that 2 in binary, it is 0 0 0 0 0 0 1 0. So if by doing a logical shift left, we are inserting 0 to the LSB and MSB bit will go out. So now it is 0 0 0 0 0 1 0 0, that is 4. Okay, so we'll see that. Okay, yeah, okay. So you can see here R7 is 04. Can you see this? R7 is 04. Okay, R7 is 04. Okay. I told we'll see with the MVN also, so we'll use that MVN. Okay, go to debug. Now the first step is, that is moving 2 to R5. Second step is moving 7 into R7, and the third step is, now the third step what it should do, it should first shift the R5 register content. Okay, see, we are moving complement of R5 to R7. But as see this block diagram, as what we are telling here according to this block diagram is the first number is directly coming into the arithmetic and logic unit. The second number will go to the barrel shifter. So according to our program here, the barrel shifter operation is this. So second number, first it is going to the barrel shifter. Okay, so first it is going to the barrel shifter. So what is there in R5 is like 0 0 0 0 0 0 1 0 in binary, right? The hex height is 0 2. Okay, so if we are shifting left logically, this will become 4, right? Okay, this will become 4. Now what is the complement of this? The complement of this is 1 1 1 1 1 0 1 1. So what is this? 1 0 1 1 is B. This 1 0 1 1 1 is B. So this is F. So F B. Okay, so F B, and all the upper bits are 0, so it is F F F F F F B. So we should get that as a output. We'll see whether we are getting that as a output. Okay, see here we are getting F F F F F F B. Can you see that? Should I zoom it? Okay, I'll zoom it. Yes. Okay, so we are getting there F F F F F F B. Okay, so whatever logical operation we are doing, what data transmission operation we are doing, that will move the second source value first to the barrel shifter, then it is moving that into the arithmetic and logic unit. Okay, so barrel shifter, what is the operation of barrel shifter? It is to shift logical left or right. Now we'll see different type of logical uh, logical or shift operations. Okay, so we'll go back to the slide. As I already explained, we have uh, 5 type of logical shift. Okay, we'll see one by one each. So we'll use the same program so that we can understand better way. um, First one, LSL, we have already seen. The next one is LSR. Okay, so we'll come back to the program. Here in the program, instead of LSL, I'll use LSR. Now what LSR will do, it will shift right. So what it is going to shift right? My R5 content is, wait, okay, yeah, my R5 content is 0 0 0 0 0 0 1 0 in binary, right? So what it is going to do, it is going to insert 0 in the MSB. So it is shifted right, and it will emit leave that the LSB bit. So what we are getting? 1. Okay, so first time when I'm shifting right, I'm getting 1. We can see, I'll execute this program, then we can see the output. Okay, again 7. Okay, executed 2 instruction. R5 value is 2, R7 value is 7. Now what this last instruction will do, it will move R5 content left logical shift right. Okay, again I used your move negative. So okay, I'll explain this first, then I'll use that MOV. Okay, so R5 content is 0 2. So if I execute this now, okay, yeah, if I execute this, I'm getting here FE. That is because what I told is I should get 0 1, right? How? 0 0 0 0 0 0 1 0. This is what there in R5. Okay, so if I shift right, this LSB bit will go out and 0 is inserted to the MSB bit. So this is what we should get. Now what is this? This is the 1, right? 0 1. So 0 1 should be moved to R7. But what I am doing here, I am not moving R5 content, I am complementing R5 content and copying into R7. So complement of this, that is 1 1 1 1 1 1 1 0. Okay, so what is this? 1 1 1 0 is E, and all the remaining upper bits is 1, so it is F F F F F F E. Okay, so what we are getting is that F F F F F F E, because I am using here MVN. So logical shift right, what it is doing, it is emitting the LSB bit and inserting 0 to the MSB. Okay, directly go to the next one, that is the next one is LASR. Okay, so with the move instruction, I'll explain. You'll understand better if I use the move instruction. Okay, so I use move instruction, and this is arithmetic shift right. Okay, ASR, arithmetic shift right. What arithmetic shift right will do? It will move the data, but arithmetically shifting right. Okay, so okay. Wait. Okay, yeah, now first we'll build this. Okay, debug, execute first two instruction. So R5 value is 2, R7 value is 7, and okay, already seen here what we got. R7 is 0 1. Why we got R7 is 0 1? That is because if I write this 0 2 in binary, okay, so this is what is stored in R5. What is stored in R5? It is starting with the MSB byte is 0, not MSB bit. Okay, MSB byte is 0. MSB, if byte is 0, MSB bit also is 0. Why? Byte means it is 0 0 0 0. So okay, so MSB nibble is 0. So it is the MSB bit also is 0. Okay, now if MSB bit is 0, it is going to insert 0 into the shifting right. Okay, so it is going to insert 0 into the MSB bit, and all the other bit will shift right. Okay, so we are thinking that it is doing the same operation, but actually it is not. Okay, so we'll give some other data so that we can understand better that R5, instead of 0 2, I'll write 8 0 0 1 2 3 4 5 6 7 8. Okay, so 1 8 0 0 0 0 0 0 2. How many hexa digits are there? 8 hexa digits are there. 8 hexa digit means it is a 32-bit number. So I'm storing a 32-bit number directly to the R5 register. Okay, so if I do that, now first I should write this hexa number I'll go to the debug window. Okay, now I'll write this hexa number in binary so that you can understand better. 8 is, if I write in binary, it is 1000. Next, the remaining zeros I'll write in binary again, 0000. That is for first 0. Like that, how many zeros are there? 1 2 3 4 5 6 zeros. Okay, so 1 0 is over, second 0, third 0, fourth 0, fifth 0, sixth 0, the last one is 2, so it is 0 1, sorry, 0 0 1 0. Okay, so this is what our binary number. Okay, I'll show in one window only properly. Okay, yes, yeah. Now this is what the binary number. Okay, so if this is a binary number, now by doing a arithmetic shift right, okay, what arithmetic shift right will do, we'll see that. First, okay, step, first value, that is R5 is loaded with 800000002. Okay, next R7 is 7. Okay, now what this arithmetic shift right will do, it will check what is the MSB bit. What is the MSB bit? MSB bit is 1, so it is going to insert 1 into the MSB bit. So first it will check what is the MSB bit, and it is going to insert 1 into the MSB bit, and the LSB bit is emitted out. Okay, so this is the number what I should get. So what is this number? This number is 1100. 1100 is what? It is 1100 is C, right? Okay, 1100 is C, so I should get C 000001. We'll see whether we are getting that C. Okay, so yes, you can see here R7, R5 content is moved 1 bit right, shifted 1 bit right using arithmetic shift, means MSB bit is not changing. Okay, so it is going to insert what is there in the MSB bit. So in the previous example, MSB bit, it is inserted 0 because 0 was the MSB bit. Okay, okay, so it is about the arithmetic shift right. Now we'll go to the next shifting operation. What is that? ROR. Okay, now all these okay, I'll come back to the, yes, yeah. Okay, now instead of ASR we are using ROR, means rotate right. Okay, so it should rotate right. So what is the difference rotate right and logical rotate is? Let's see that. Go to the debug first. Okay, now step, second step and third step. Okay, so we are executed all the 3 instruction. So in the first step it is 8000002, R7 is 0 7, and this one rotate right, it is going to rotate R5 register content. Now for this we have to see the CPSR register also. So in the CPSR register, what is the carry bit? That is important. Okay, so it is rotating right. At that time, what is there in the LSP? What was there in the LSP? If I write in binary, this one is the last bit. I'll write last 4 bits, that is 0010, right? For 2, the binary is 0010. What will happen? It is rotating right, means the LSB bit of this 2, that is this, is moved to the carry bit. Okay, so if it is moved to the carry bit, and we can see there R7. What is R7? It is 4 0000001. Okay, okay, first I'll write in binary, then you can understand properly. So it is 1 0 0 0 is 8. Next 0 0 0 0 0 0 0 0 2 0 over 3 4 5 6. Okay, so this is my uh, binary number for R5. R5, what hexa number is there? In binary representation, this is my number. Okay, so what this will do, it will not emit the LSB bit. All the shift left, shift right, all these are emitting that LSB bit or MSB bit, right? So but in the rotate operation, it is going to rotate, means this 0 is going to be inserted, like from here it is inserted to the MSB. So this 0 will come as the MSB bit. Okay, 0 will come as MSB bit. If 0 comes as MSB bit, then this number is like 000100, that is 4. So 0000, last one is 1. So that is what we are getting in the R7 register, that is 40000, last one is 1. Okay, yeah. Next, I'll use the same ROR, but 2 bit. Okay, 1010 is what? 1010 is A. So all the remaining bit is 0. So that's why we are getting here A 00000. Okay. Next, the carry flag is uh, affected? No, the carry flag is not affected. Okay. Okay. So this is the use of barrel shifter. So in the barrel shifter, it is how it is shifting left is shown here. The 4 other mnemonics of that barrel shifter is we have seen. The next is arithmetic instruction. The arithmetic instruction, I am using the first instruction, that is ADC. Okay, before using that ADC, I'll use this add instruction. Okay, so it is easy for me to explain. Okay, so will you see we'll use the same program. Instead of move, I'll use ADC. So syntax for ADC is add, okay, add. We'll see that syntax again. Here syntax is instruction, condition, S suffix, destination, source, and source 1 and source 2. Okay, now I want source 2, sorry, destination is R8. Okay, and source 1 is R7 and source 2 is R5. Okay, I'll use R5 as source 2, R1 is R7 is source 1 and destination is R8. So this instruction will copy add data of, first I will change the number. Okay, so R5 is 2, R7 is 7, so after addition 7 plus 2 I should get 9, and that 9 is stored in R8. Okay, so 9 is stored in R8. Okay, arithmetic instruction, that syntax is, okay, we are use the same syntax. Now R5 value is 2, R7 value is 7, so after addition we should get that value. We'll come back. Okay, R5 is 2, R7 is 7, after addition we are getting 9 in the R8 register. Okay, so it is doing a addition. Now come out of this. Okay, so next instruction for add, that is adding to 32-bit value and carry. Like if there is any carry bit, so it will add that with the previous value. Okay, so for this I have to show different example, I guess, because I have to set the carry flag. Let's see here, I'll use one number, that is 8 0 0 0 0 3 4 5 6. Okay, 80 0 0 0 0 0 2. This is also same number, that is 8 0 0. Okay, now addition of these two number, like I am storing that again back to the destination, that is R7. I'll use one more instruction, that is ADC R8 comma R7 comma R5. Okay, now addition of these two number, that is like the first R7 is 80000007 and R5, that is 80008. Now when if we are adding 8 and 8, okay, so 8 in the binary, that is 1000. Okay, I'll write in down 8 in binary, this is 001000. If we are adding this with 1000, so answer is like under 0. Okay, this is 1 0 0 0 0. Okay, because addition of 0 and 0 is 0, addition of 0 and 0 is 0, addition of 0 and 0 is 0, addition of 1 plus 1, 0 is the answer and 1 is the carry. So this will go to the carry flag. Now whether it will go to the carry flag, we'll see that first. Okay, actually the first addition will generate a carry. Okay, so I want to see whether it is generating carry. Yes, it is generating a carry, but whether it is going to set the carry bit. Okay, yes. Okay, so first one, R5 is the number what we are given. Sorry, I have not built it, so that's why we are not getting the proper answer. Okay, so build it. if we are doing any changes, we have to build it, otherwise we are not getting the updated program output. Okay, now R5 value is 80002, next R7 value is 8777. Okay, now addition of these two numbers, 2 plus 9 is 2 plus 7 is 9, and this one we should get 0 and carry is 1. Okay, so we should get, we'll see here, see, we are getting in R7 the MSB bit is 0. It is 0 is yes. Okay, so R7 MSB bit is 0. Okay, so if MSB bit is 0, uh, it should generate a carry, is it? So we'll see whether it is generated a carry. So if I go and check here, the carry flag also is not set. Got it? So why it is not set, the carry flag? Because we'll go back to that slide. Here the s suffix with the arithmetic instruction, I should use the s suffix to update the, what is the use of s suffix? To update the current program status register. So for updating a current program status register, we need a s suffix. So what changes I should do is, here I should use ADDS. If I use ADDS, then it is updating the carry flag, because this addition is generating a carry, but carry flag was not updated, right? The carry flag was not updated because f suffix was not there. Now we'll see. So addition is done. We'll see whether it is updated the carry flag. Okay, so the third step, that is ADDS. Now R7 value is 8000007, and R5 value is 8000002. Now if we add this by adding 7 plus 2, I'll write the answer here, like by adding, I'll write from the beginning, that is the 8 plus 8 is 16, means in hexa it is 10. So 10, next 0 plus 0 is 0, 0, 0, 0, 0, 0, 9. Okay, so this is the answer. So here 0, 0, 0, 0 to 9, this value will be stored in R7 by after execution of ADDS. So 1 should be stored in carry flag, because we are use the s suffix. The previous method, like if I use only ADD, it is not going to update the carry flag. Now see here, R7 is 00007. I'll zoom it and show you. Can you see there? R7 is 0009, and now we should check the carry flag. Carry flag. Okay, come back to this. Now we should check the carry flag. Carry flag bit also is 1. Okay, yeah. So that is the addition of the first add instruction. So this add instruction not only adding, it is generating. If there is a carry, it will generate the carry, and if it is generating a carry, it will update the current program status register. Now the second instruction, that is, I mean, one more add instruction, that is add with carry. So now here we have two registers. What is that? R7 and R5. So R7 value, the present R7 value is, we can see here, it is 0009. So R7 value is this 0009. Then R5 value is 80002. So R5 value is 80052. So this is the two number what we have now. Okay, now it is not only adding these two number, but in the instruction we are showing only two register, that is R5 and R7, but instruction says that we should add with the carry. So we should check what is the carry bit. Now what is the carry bit? Carry bit, we know that it is 1, right? So carry bit is 1. So if we are taking that carry bit, so 1 also we should add with this. So if we are adding this, we are getting 9 plus 2. 9 plus 2 is, after 9, A, B, next plus 1 is C. So answer is right answer. It is 8 plus 0 is 8. So 0, 0, 0, 0, 0, 0, C. So this is what it should be answer. Okay. So we'll execute this instruction, then we'll see what we are getting in R8. Now we can see here in R8, before executing that instruction, R8 value is 0. Okay. So before executing, it is 0. Now we should check. Sorry. Okay. Before executing, it is 0. Now after execution, we should check what is the output. So the output is 8000. And you can see, zoom it. Okay. So R8 value is R8 value is 000C. Okay. This is about add and add with carry instruction. Okay. Now we'll see this subtract instruction. So for subtract instruction, we should use SUB. We'll go back to the same program. Here, instead of, sorry. Okay. Now I should use the subtract instruction. So only I used SUB. Okay, SUB without S suffix, and R8 is my destination. Now, according to this program, it should subtract R5 value from R7 value. I'll change the number. Change the number. Okay. 02 and 07. It is easy to understand if you go with the smaller number. Okay. So build it. Okay. So go to the debug window, then so first two instruction, loading 2 into R5 register. Okay, the next instruction is loading 7 into R7 register. So subtract instruction, that is, this is source 2, right? R5 is a source 2, R7 is a source 1. So it will subtract, yeah, okay. So in R8 we are getting 5, that is because it is subtracting 2 from 7. So 7 minus